This is going to begin our discussion of PIC24 hardware timers. Recall that a timer is just a counter. Time can be converted from elapsed time or ticks by multiplying by the clock period of the timer. So time is equal to ticks times the clock period of the timer. If a timer is a 16-bit timer and it is clocked at an instruction cycle frequency of 40 megahertz, then it will count its full period, that is from 0 to quad FF and back to 0, which is 65,536 ticks, in this time 65,536 ticks times 1 over 40 megahertz, which is 25 nanoseconds. That time will be 1,638,400 nanoseconds, or 1.6384 milliseconds. This time it takes for the timer to count from 0 to quad F and back to 0 again is called the rollover time, and this value right here is equal to 2 to the 16th because the timer is 16 bits wide. This rollover time here can be increased if I slow down the clock. If I slow down the clock, I increase the time period. This slide shows the block diagram of the timer 2 subsystem in our particular PIC24 variant. There's also a timer 3 subsystem that is practically identical to this one, and the PIC24 actually has other timers as well. Let's make some sense of this diagram. This multiplexer right here selects the clock source for our timer. We can either use the internal instruction clock or an external pin. We're always going to use the internal instruction clock in our examples. This block right here is called a prescaler. What it is used for is for dividing this clock down, which increases the clock period of the timer. Increasing the clock period will increase the rollover time of the timer. Notice that this prescaler has 4 different choices that it can be set to. A 1, divide by 8, divide by 64, or divide by 256. The larger the number, the slower that the timer is clocked. Here's the timer register itself. It's a 16-bit timer. We also have this thing called a PR2 period register. What this is used for, it's used to control the rollover time of the timer. On the previous slide, we talked about the timer when it reached its maximum value, it rolling back over to 0. But in this timer, the way it works is that we're going to add a value, we're going to load a value into the PR2 register, and when this thing is equal to timer 2, then it's going to cause the timer to reset back to 0. So for example, if we loaded this PR2 register with an 8,000, then when this timer got equal to 8,000, it would roll back over to 0. Finally, there's going to be a line out of this comparator that says when this thing rolls over, what we're going to do is we're going to set a flag associated with this timer called the T2 interrupt flag, and this can be used to generate an interrupt on timer rollover. We're going to want to use timer 2 to generate an interrupt after a particular amount of time by setting this timer 2 interrupt flag. When this timer 2 interrupt flag becomes set, it becomes set when the timer 2 value becomes equal to the constant value in the PR2 register. When that becomes equal, then this is asserted, and we're going to set the flag and reset this timer. We can write the amount of time that it takes to set that flag via this equation. We take the value in the PR2 register and add 1, because it turns out that it takes an extra clock cycle to reset the counter back to 0 and to set this flag, and we're going to multiply that by the period, the clock period of the timer. The clock period of the timer is going to be the instruction cycle period times the prescale value. Because we know that period is equal to 1 over frequency, we can represent this by prescale value divided by the instruction clock frequency. Both timer 2 and PR2 are 16-bit registers, so the maximum value you can write to PR2 is quad F, which is 65,535. If we plug that in this equation and add 1 to it, we get 65,536, which is equal to 2 to the 16th, and this equation here is exactly equal to this equation that we used back here. Generally, we're going to know the amount of time that we want to generate the interrupt for, and that means that we're going to have 2 unknowns in this equation. The clock cycle, the instruction clock cycle period will be fixed. So what we will generally do is we'll set the prescale to some value, either 1, 8, 64, or 256, and then we'll solve for the necessary PR2 value to get some particular time. So solving for PR2, we get this equation right here, which is going to be the equation that we're going to end up using a lot in order to actually determine the PR2 value necessary to get a particular timeout value. So let's do some example calculations. Suppose that we want this timer 2 interrupt flag to be set after 15 milliseconds and that our instruction cycle frequency is 40 megahertz. If we take this value and this value here and also take prescale and plug that into this equation here, what we'll find out is that PR2 here is equal to 600,000. This is actually an invalid value because 600,000 does not fit in 16 bits. The largest value that we can write to the PR2 register is 65,535. So this particular value of prescale is invalid. We'll go to the next prescale up, which will be 8, and we find that PR2 is 75,000. This is still invalid as it's greater than 65,535. We plug in prescale 64, and now we get a value of 9375. It turns out that, so this would work. If we plug in a value of 256, we get a value of 2344 for PR2, so this would work as well. Generally what you want is you want the lowest prescale value that will give you a valid PR2 value, because this will give you the most accurate timing. So if we set our prescale value to 64 and wrote a value of 9375 to PR2, and we had an instruction clock cycle frequency of 40 megahertz, and this would mean that every 15 milliseconds this flag would be being set. And if we had this interrupt enabled, we'd be getting an interrupt every 15 milliseconds. Configuring timer 2 to interrupt every interrupt timer period like this is called a periodic interrupt. In order to make use of timer 2, we must configure it first by writing values to its control register. This diagram is a standard way that PIC24 datasheets shows configuration bits for control registers. Each bit is named. This is bit 15, this is bit 14, this is bit 13, and so forth. This information right here tells you, the RW says that this bit is both readable and writable. This -0 right here says that this bit is going to be reset to a 0 at system reset or power on. Let's look at some of these individual bits. This bit right here, T on, which is the most significant bit, bit 15, when it's a 1, it's going to start the timer. When it's 0, the timer is not operating. This corresponds actually to this bit here in this diagram. When it's 1, recall that a 1 on the input to an AND gate, 1 AND with anything is anything that's going to allow this signal to pass through, and this is going to be our clock. So when this is a 1, our clock is going to clock through here, and it's going to clock our timer, operating a timer. If this is a 0, then that means that this signal right here will always be a 0, and the timer will not be incrementing. It will not be in operation. This bit right here, TCS, when it's a 0, it's going to select the internal clock as a clock source. If it's a 1, it's going to use that external pin. So we're actually going to use the internal clock source for our example. So this bit will always be a 0. This bit right here, bit 13, is a power saving bit. When it's 0, this module is going to continue operation in idle mode. Recall that idle mode is a power saving mode in which the CPU clock stops, but all the clocks keep going to the peripherals. If we program this bit to a 1, then we can actually turn this peripheral off when we're in idle mode. We're not going to care too much about the setting of this bit in our examples. We're going to keep it at 0 for our examples. This bit right here, the T-gate bit, we're not going to discuss this mode of operation. We're always going to keep it at 0, which means that mode is going to be disabled. This bit field right here is important to our examples. This sets the prescaler. A 1-1 selects a prescaler at 1 to 256, 1-0 64, 1 as an 8-bit as 8 prescaler, and a 0-0 is a prescaler value of 1. This bit right here, the T32 bit, which is bit 3, if it's 0, then timer 2 and timer 3 act as two separate 16-bit timers, which is what we're going to do for the majority of our examples. You can actually join these two timers together and have them form a single 32-bit timer. To program the timer 2 configuration register, one way to do it is simply write a 16-bit value to it, like here. Here, the name of the timer 2 configuration register is T2con, and we're simply going to write this 16-bit value to it. This 16-bit value is going to turn the timer off, set the prescale to 64, and select the internal clock. In our example, however, we're going to use a more readable form like this, in which we're going to take a bunch of macros that have been defined, and we're going to bitwise OR them together. So this is saying turn the timer off, select the idle configuration such that it's on in idle, set gated mode to off, select 32-bit mode to off, select the internal clock source, and set the prescaler value to 64. Where are these macros defined? They're actually defined in this file right here, pic24 timer.h, and they have these values as associated here. If we actually do that bitwise OR together, here T2 off, if we go back and look at that, that's defined as 0. T2 idle configuration, let it be on during idle. That's also a 0 as well. If we bitwise OR all these fields together, we're going to end up getting the same value up here as a 20. Why is selecting a prescaler of 64 equal to this hex value right here, 20? Well, if we take a look at this, a prescale value of 64 is going to be a value here of a 10. If we write this in hex, this is going to be 0. These 4 bits right here is going to be 2. These 4 bits right here is going to be 0, and these 4 bits right here is going to be 0. So for selecting a prescaler value of 64, the 16-bit value is going to be 0020 as defined here. So we're typically going to use this more readable form to set the configuration register. You can also access individual bit fields like this. 22con bits.ton set to a 1. What that's going to do is going to set the ton bit here to a 1 without affecting any of these other bit fields, and we'll do that as well. Let's use a timer 2 that's generating a periodic interrupt every 15 milliseconds to generate an output square wave. The way that we're going to do this is that we're going to use an output. In this case, we're going to use RB2, and we're going to write a ISR for a timer 2 interrupt. And every time this is called, which is going to be called every 15 milliseconds, every time the timer 2 interrupt flag is called, what we're going to do is we're going to take this output, which we're going to call via a macro called wave out, which is going to be equivalent to _lat b2, and we're going to toggle it. That means that every 15 milliseconds, this output is going to go from 1 to 0 and back to 0, generating a square wave. We're also going to clear the timer 2 interrupt flag in this ISR, as we do of all interrupts. So in order for this to work, we need to configure timer 2 to generate an interrupt every 15 milliseconds. That means the output pin will be toggled in the ISR every 15 milliseconds, which means the period itself will be 30 milliseconds. So let's write some code. We're going to call it config timer 2, and this is going to configure the timer for that operation. The first thing we would do is we're going to write a value to the T2 configuration register as specified in the previous page. That's going to have the timer off, 30-bit mode off, and so forth, and it's going to set the prescaler value to a 64. The next thing we would need to do is we would need to set the PR2 value to some value such that the interrupt flag would be set every 15 milliseconds. But what is that value? Well, we calculated that on this previous page here. We said that if the instruction cycle frequency was 40 megahertz, which it is on our demonstration board, and our prescaler was 64, then this value right here at 9375 written to PR2 would give us this 15 millisecond period for our timer 2 interrupt flag. So what we could do is we could simply write a line here that would say PR2 is equal to 9375, and we would be done with it. However, what if we later on decide to change this to, instead of a square wave of 30 milliseconds, we wanted a square wave of 20 milliseconds? That would mean that this interrupt would have to be generated every 10 milliseconds, and we would need to recalculate and change this value. In order to make this code more portable, let's do something here in which we're going to define a macro called ISR period. There's going to be a value that's going to be in milliseconds, 15, and what we're going to do, instead of hard coding in this value for PR2, we're going to calculate this value. How are we going to calculate this value? We're going to use a library function that we supply for you called ms to u16 ticks, which is going to take this value in milliseconds and it's going to convert that to equivalent timer ticks depending upon the timer prescale value that we're going to pass into it. So this function here, if we pass in the value of the timer 2 configuration value, it will actually extract the timer prescale value from the timer 2 configuration register, and this value here, this function, is going to be the number of timer ticks that is equivalent to this value, which is 15 milliseconds. This function is also going to know our current instruction cycle frequency as well. That is not going to be equal to the PR2 value. Remember, in this equation, we had PR2 plus 1, so what we're going to have to do is we're going to take this tick value calculated here by this function and subtract 1 from it in order to get the actual PR2 value. This will give us a flexible method of setting the PR2 value. Later on, if we wanted to change this ISR period, all we'd have to do is change that to something else, and the PR2 value when we execute this code would be automatically calculated for us. The remaining lines in our config timer 2 function does the following. This line right here, timer 2 equals 0, is going to clear the timer 2 register. That's actually the special function register of the timer itself. It's clearing this value to 0 so we start counting from 0. This next line, these next 3 lines here is going to configure the interrupt. First of all, we're going to clear the timer 2 interrupt flag, which is always good practice. These 2 lines are then going to enable the interrupt by first setting the priority to something greater than 0. Here we arbitrarily chose 1, and now we're going to also set the interrupt enable bit to a 1. At this point, the timer interrupt is enabled. However, the timer is not yet counting up because here this guy right here has set the timer to off. We still need to turn the timer on. We need to enable it. So here we're going to do that by this line. We're going to do t2con bits.ton is equal to a 1. At this point, this is going to allow the clock to reach the timer. So now the timer is now counting after this line is executed. One thing about this particular library function, since it's reading the timer prescale value out of the timer 2 configuration register, you need to write the timer 2 prescale value before you actually call this function and pass in the configuration register value. Let's look at what's happening in our main. We're first going to do config basic as we always do. Then we're going to configure our parallel I/O, which is essentially configuring our RB2 output to be a digital output here. Then we're going to call our config2 timer code, which is this. At this point, our timer is now counting up. This while loop here is simply going to call the do heartbeat code. It's not doing anything because it turns out that our interrupt serve routine and our hardware timer is doing all the work. There's nothing for this while one loop here to do. Every 15 milliseconds, what's going to happen is the timer 2 flag is going to be set. The interrupt is enabled, so the ISR is going to be called. We're going to toggle the output line here. I'm going to clear the flag and then exit the ISR. So here's the interrupt service routine is essentially doing all of our work. So here, let's see this in operation. Here I've programmed my PIC24 with squarewave.c and it's now operating. Of course, there's nothing to see here because everything is happening on the output pin of the RB2. There's a square wave being generated, but we can't tell it from here. We got to put a scope on the output pin, which I've done here. So here's a scope output. You can see that it's going from about 0 to 3 volts. Here is going to be the ISR period that we're measuring. It turns out that period is about 14.9 milliseconds, which is pretty good considering that we're using the internal RC oscillator instead of an external clock frequency for accuracy. So the period of this thing is actually going to be 30 milliseconds at the square wave. Let's do that. That's about right. So here we got about 29.844 milliseconds. Let's assume that we wanted to have a faster ISR period. So I'm just going to change this to 5 milliseconds. That means the period of our square wave is now going to be 10 milliseconds, and I'll recompile and reprogram the PIC24 this new code. So I've reprogrammed the PIC24 the new squarewave.c code, so now I should have a faster frequency on my output pin. So let's take a look at that on the scope. So here I'll bring it up, and yes, the frequency is higher. If I go ahead and measure this roughly, what I'll see is here I'm going to go from rising edge to rising edge. I do see that it's about 10 milliseconds. In closing this video, I would like to say a few more words about this library function, milliseconds to U16 ticks, that takes milliseconds in and returns the number of timer ticks for a particular prescale value. This is an important library function. We use it in several of our examples. And this library function is found in the file pic24_timer.c, and internally it uses floating point calculations for accuracy. However, floating point calculations takes a lot of time to execute, and so you should not use this function in a time critical application. If you have the need to dynamically switch PR2 values rapidly, then you should simply pre-compute those values and assign them to PR2. The two other things to note, internally, this function understands what the instruction cycle frequency is, because that is fixed at compile time when you use our library functions to choose a clock source. You can see our library documentation for more information. Finally, when the tick value is computed, if it does not fit in a 16-bit variable, then you will get an error message. What that would mean is that you'd have to change your prescale value, typically increase it, in order to get a ticks value that fits in 16 bits. There's an accompanying function, microseconds to U16 ticks, that takes in microseconds and then returns clock ticks. This function here takes milliseconds in and returns clock ticks. So this can also be useful in some situations.